Okay, so today we are doing chapter 3, force and motion. Our projectile, motion, free fall and all that dah settle Kita dah belajar pasal linear kinematics. We already learned about resolving in the x and the y. Tak kisahlah apa jenis vektor sekalipun, whether it's like a single vector yang ada angle ataupun a projectile motion or a free fall, we can always resolve it into its x and y, except for free fall lah. Free fall dia one exist je kan. And then we talked about linear motion and you guys have to remember that soalan yang chapter 2 ni, it is preferable if you draw your motion before you start doing the question. Acceleration equal to berapa, kat sini acceleration berapa, u, v, v1 and then we have the v2 over here. Okay, so always start with these diagrams so that you don't make mistakes in your web assign or in your exam later. Okay, so semua yang kita belajar from chapter 1 and chapter 2, kita akan apply balik in chapter 3. Specifically resolving the vector resolving lah. Vector kita belajar, asalkan ada vector je, ada resolve lah. Resolve in the x and the y. Okay, so for chapter 3, which is on force and motion, kita akan belajar about inertia and momentum. I'm recording, right? Yeah. And then Newton's law of motion, we have 3. And then forces on object. And then object in equilibrium, maksudnya it is staying still ataupun staying at rest, ataupun V is constant. So this is when object is in equilibrium. Kita akan tengok problems related to that, and also objects in linear motion, the changing velocity, ada acceleration. So kita akan pakai balik all those that we have learned so far. Alright. So after completing this chapter, this is your learning outcome. You have to know how to define inertia, what is mass in general, what is momentum. You have to know, you have to state the Newton's law of motion. Some other the first one, second one, or third one, and then identify the forces acting on an object and sketch its free body diagram. Yang ni yang selalu orang mess up. And when you mess up this free body diagram, you will mess up your equations. Daripada free body diagram ni, kita akan tulis our equations. It comes from our free body diagram. Equation tu tak datang daripada thin air. So we have to draw our free body diagram and then our equations. And then the equations depends on whether the object is moving, ada acceleration, ataupun it's not moving or at a constant velocity. So those equations will be affected by the situation. Okay, so inertia. Inertia is the natural tendency of an object to remain at rest or continue its state of motion. So if I'm sitting, I am at rest. My V is equal to 0. So it is hard. It is hard for me to get up from my chair. So I have that natural tendency to stay in my chair because malas, right? Or if I'm jogging and then I'm jogging at a certain pace, my pace is 7 kilometer per minute, contoh, that's not my real pace. So I'm jogging at 7 kilometer per minute and I feel like that is my comfortable pace, right? So it's hard for me to slow down or actually go faster because of inertia. So when you have achieved a state of motion, you like that motion to happen continuously unless tu nanti kita sambung kemudian. So inertia is the natural tendency of an object to remain at rest or continue its state of motion. Object at rest, you need a force to move the stationary object. An object in motion, you also need a force to change the object's velocity, to make it slower or faster, or to stop the motion ataupun change direction. So apa-apa yang berkaitan dengan change, berkaitan dengan motion, sama ada tengah duduk diam-diam ataupun tengah ada certain speed, you need a force to change it, either direction, either speed, or either to make it stop ataupun move. Okay, so inertia is related to mass in the sense that if you have a bigger mass, your inertia is bigger. If you have smaller mass, your inertia is smaller. Saya kecil, so inertia saya kecil. Saja nak cerita, tak adalah. Tak ada, saya tak kecil pun. Okay, so mass is related, inertia is related to mass, right? So if you are bigger in size, you have a bigger inertia compared to your friend that is smaller. And then to quantify inertia, we use the word momentum. To quantify inertia, we use momentum. So momentum ni berkait rapat dengan inertia. Inertia ni is like the concept of it. Momentum is how you quantify. What does quantify mean? It means that you can calculate for something. So momentum ni related to how heavy or light an object is and how fast or slow an object is. So the heavier your object, the greater momentum you have. Or the faster your object, the greater momentum that you have. A greater momentum that you have, a greater inertia that you have. So the quantity that measures inertia is called momentum. So now I'm introducing to you this equation. P equals to mv. P is momentum. P is specifically for momentum. Tak ada benda lain unless pressure. Tapi kita tak belajar pressure dalam chapter ni. So P can be momentum or pressure. Tapi pressure bukan vector. So kita cakap pasal pressure, kita cakap pasal vector sekarang kan. So momentum is P. P is equal to mv, whereby m is mass and v is velocity. So just now I told you, the greater your mass, the greater your momentum, the greater your velocity, the greater your momentum. So increasing your m increases your momentum based on this equation, and increasing your velocity also increases your momentum. If you want to decrease your inertia or decrease your momentum, you need to have a smaller object, or like a lighter object, sorry, not smaller, lighter object, or an object that does not move too fast, or a slower velocity. Okay, so P equals to mv. This is the equation. So an object will remain at rest or move with constant velocity, that is constant in magnitude and direction, unless acted on by a force. So this relates back to its natural tendency to remain at rest ataupun move at a constant speed unless acted on by a force. This is called the law of inertia, or Newton's first law. So if they ask you, okay, what is Newton's first law? It is the natural tendency of an object to remain at rest or move at a constant velocity unless acted on by a force. And then we move on to our Newton's second law. What is the relationship between force and momentum? So in general, all moving objects has momentum. So P equals to mv. And if your v is equal to 0, therefore your p also equals to 0. So all moving objects has momentum. If they don't have motion or they don't have speed, then they won't have momentum. So we need force to change its velocity. We need force to change its velocity. Change in velocity, delta v. So why is that? We need force to change its velocity, to stop or to make it slower, or slower to change its direction. Okay, you know this. To change its motion lah in general, hence changing its momentum. So we need force to change its velocity and to change its momentum. Sorry. So why is that? Because when we have a change in velocity over the change in time, we actually have acceleration. And when we have acceleration of a mass of an object, this is F equals to ma. So F equals to ma, or force, only happens when you have a change in velocity over time. When you don't have that change, then acceleration equals to 0, then you don't have force. So you need to have that change in velocity to have force, or you need force to change the velocity, it goes vice versa. So we need a greater force for a quick change rather than a slow change. I think this makes sense. Kalau kita tengah bergerak, lepas tu saya terlanggar, saya nak cakap Haikal tapi nanti berdosa pula. Okay, saya terlanggar tiang yang kecil lah kan, tiang yang tak berapa berat, tak berapa besar mass dia. So saya ada macam velocity saya tak adalah terus berhenti terus. Tapi kalau saya langgar dinding yang sangat besar, mungkin saya akan, macam nak cakap kita tak masuk impact lagi. Okay, tak apalah, kita just take this as it is lah. We need a greater force for a quick change rather than a slow change. Kita tak masuk lagi impact. So impact berkaitan dengan langgar benda nanti. Okay, so the general form of Newton's second law, the rate of change of momentum of an object is directly proportional to the force acting on it. So here F is proportional to the change in momentum over the change in time. So now you're asking me, Doktor, macam mana tiba-tiba ada time kan? When we have something changing, it's always going to change over time. Ada tak kita tengah buat something, masa berhenti? Tak ada kan? Everything happens during when time changes, when the time stops, that only happens when we take a photo. We take a photo, oh gambar ni masa Haikal tengah makan. Okay, waktu ni berlaku pada 10 AM. So itu adalah kita stop masa, ambil gambar, that is we captured the photo at that certain time, but it doesn't mean that we stop time. Time is still moving. Masa saya tunjuk gambar Haikal tengah makan cokodok ni ataupun Amy tengah makan cokodok ni, waktu tu dah pukul 10.30. Time keeps on moving. So whenever there is change happening or whenever there is nothing happening, time still moves, right? Time still moves. It doesn't ever stop. It's linear and it keeps on moving. So whenever we talk about change, there will always be a change over time. Something change in momentum over time, change in velocity over time. Tiba-tiba ada time, tiba-tiba ada time. Memang time is constantly moving. So almost everything is over change in time. Okay, so here force is parallel to the change in momentum over the change in time, which is also equal or. So sebenarnya dia tak adalah, dia proportional tapi dia also equal. Selalunya kalau kita cakap pasal proportional, dia akan ada constant tau. Contohnya F is proportional to displacement, delta, change in displacement. But this is not the equation. The equation is F is equal to K delta X. So selalunya kalau kita cakap pasal proportional, akan ada constant for the equation. But in this case, F is proportional to delta P over delta T, but it is also equal. Maksudnya tak ada constant lah kat depan tu. Okay, I'm just introducing that to you guys. Nanti later on in other chapters when we talk about proportionality, it doesn't mean that that's the equation. It does not mean that it is the actual equation. Sometimes it can be, but most of the time it's not. Okay, so if F is proportional to the change in momentum over the change in time, how do we expand this? So dp dt, I told you before, delta is actually change and d is also change. The differentiation dp, contohnya you're differentiating momentum, right? dp dt, you are differentiating momentum with respect to time, but the d refers to a small delta. You are differentiating over a small duration of time or small duration of length or whatever lah, asalkan change to small. So this D refers to something that the change that is small, whereas delta ni not necessarily small. So delta ni, it can be big, it can be small. So D and delta is the same thing except that D is typically for small changes. So the change in momentum over the change in time is d dt dalam kurungan mv because P equals to mv, right? So kita substitute je mv tu. And when I'm expanding this differentiation, it's m dv dt plus v dm dt. Okay. And then if m is constant, then therefore delta m is equal to 0. Then if this guy is 0, we get rid of this term. We are left with m dv dt. And you know what is dv dt? That is basically acceleration. The change in velocity over the change in time is acceleration. This was from chapter 2. So you get your equation F equals to ma. However, this only applies if the mass is constant. But in reality, we know that our mass does not change from time to time unless kita cakap pasal bulan ni dengan bulan depan, mungkinlah saya punya weight berubah kan. But if we're talking about small changes in time, then yes, my mass is not changing unless like ada orang tu ada special ability, 1 hour later mass dia naik 10 kg. That doesn't happen to normal people. So we just assume everyone has a constant mass. F equals to ma applies to everyone and all objects. Okay, so now that is how we get our F equals to ma, which is the Newton's second law of equation for constant mass. The SI unit of force is Newton, and this is the SI unit, which is the force on 1 kilogram of mass to accelerate at 1 meter per second squared. To accelerate 1 kilogram at 1 meter per second squared. 1 kilogram refers to the mass, at 1 meter per second squared refers to the acceleration. So that is the definition here. What is force? Sorry, what is 1 Newton? 1 Newton is the force to accelerate 1 kilogram at 1 meter per second squared. So that is how they define Newton. So semua benda yang unit ni ada definition dia lah. So definition Newton was that. Okay, so what if there is a change in mass? For example, you become a scientist, a biochemist, no, I don't know. Scientist lah, scientist yang deals with biology lah. Okay, and you create an artificial being that is able to change its mass at will. Contohnya, dia boleh berubah jadi kerusi ke, tiba-tiba dia nak jadi spy ke, dia nak jadi apa? Dia nak jadi pasu bunga ke sebab dia nak jadi spy kan. Okay, ni macam merepek lah. Tapi kalaulah korang jadi scientist yang boleh create something that is able to shape-shift, dia berubah bentuk. So meaning to say it is able to change its mass. Therefore, the F equals to ma does not apply to this artificial being, right? Why are we talking about something that does not exist? Because we don't know what the future may hold. So maybe akan datang ada orang boleh buat that kind of being. Dia buat, tahulah kan, sebab kita punya makanan pun semua dah genetically modified. So anything's possible actually. So why do we have to know this? Because it's knowledge and maybe in the future we'll use it. So but now F equals to ma lah. But if there is a change in mass, then your equation becomes F equals to ma plus v dm dt. Okay? Kalau change in mass lah. If m is not constant. Okay, so kita dah belajar Newton's first law, which is law of inertia. What does that mean? It is the natural tendency of an object to remain at rest or keep its constant velocity unless acted on by a force. And then we go into Newton's second law, which talks about the force. What is the force for this change, right? The force is equal to ma, and we know that when we have force, we have a change in velocity over the change in time, or if we have a change in velocity, we will have some type of force. It goes vice versa. So we go into Newton's third law. Tadi cakap pasal force, ni cakap pasal force lagi. So if object 1 and object 2 interact, so this is object 1. It's a brick. Tak tahulah betul-betul brick ke tak, tapi brick lah dalam gambar ni. So object 1 and this is object 2. So if object 1 and 2 interact, maksudnya diorang in contact. That's how they are interacting. They are in contact. The force exerted on object 1 on object 2 is equal. The force by the brick on the table is called F12. Ni object 1 on object 2. Object 1 on 2. Okay, so it's called F12. This is the force exerted by object 1 on object 2. Is equal in magnitude but opposite in direction to the force exerted by object 2 on object 1. Okay, so kalau benda ni dia nak exert 10 kg, dia nak exert 10 Newton, table tu cakap aku pun nak exert benda yang sama. So dia akan exert benda yang sama but in opposite direction. So F21, the force exerted by object 2 on object 1 is equal but in opposite direction. This gives us this equation, F12 equals to F21, but there is a negative sign. Magnitude dia sama, the sign is different because they are equal and opposite. So this is equivalent to saying a single isolated force cannot exist. Meaning to say, if I touch this phone, right, the phone is also applying the same force to my hand, but I don't realize it. But there is a force. I apply 5 Newton force. The phone said I'm applying 5 Newton force too on your hand. So it goes, there's no single isolated force lah sebenarnya in reality. Okay. So our forces can be categorized. Oh, I have a lot of, do I have questions? Doktor terasa kalau phone tu jatuh kat hidung je. Betul. Molarity volume. Oh, ni chemistry Okay. Good luck lah. Tapi chemistry asasi rasanya okay, good. Degree bagi saya susah chemistry. Okay, anyways. Okay, so forces can be divided into two. One is external and one is internal. Kenapa dia membesar ni? Okay. One is external and one is internal. So external ni, if you have an object, Okay, if you're an object and you are pushing this object by 10 Newton, this is an external force. When you push the object, akan ada berlaku resistance or friction in the opposite direction of the motion. So this is external force. What about the weight? The weight of this object is F equals to mg. It's happening outside of the object. That is external force. Apa lagi? If this is an iron and it is attracted to a magnet, that is external force because it's happening outside of the body. So anything that happens outside of the object is called external force. Internal force is the forces that happen inside the object. For example, weak forces between the molecules, between the atoms. Yes, and also the vibration of atoms. So apa-apa yang kat dalam objek, nuclear force, weak force, vibration of atoms, that is internal forces. And for our chapter, for our syllabus, kita akan focus on external forces. Internal forces nanti, kalau nak belajar boleh ambil degree in physics or engineering, saya tak sure dia ke tak. Saya tak belajar pun. Okay, next. We have, for external forces, we have two types of forces juga, two categories. We have the contact forces and non-contact. So my face is kacau. So we have contact forces and also non-contact forces. As the name says, contact, ada sentuhan ataupun tak bersentuh. So for example, contact forces, right? This is a contact force. I'm pulling the spring. I have to touch it for me to pull it. So it's a contact force. And this is a mother tarik anak dia using a trolley. She has to have contact with besi tu, tak tahu nama dia apa, with that thing lah, with that handle for her to pull. So this is a pull force. And this is also a pull force because she's pulling, right? She's pulling, so she's exerting a pulling force. And this guy is a footballer tengah sepak. Sorry, this is rugby. Rugby, football. So dia tengah sepak. So he's exerting a push force. Sorry, ni rugby kot. Tak tahulah saya. I don't remember. So push force, right? Kalau takkan dia nak tarik pula kan? Sebab dia nak benda tu bergerak ke depan, so he has to exert a push force walaupun it's called kicking. And then we have field forces. This is between two planets, small m, big M, two planets of different masses. Let's say this is Moon and this is Earth. Moon is not technically a planet, but okay lah, boleh masuk dalam gravitational force. So Moon and Earth, they have gravitational force acting between them. Are they in contact? They're not in contact. If they are in contact, we would die because awak kena empak bawah Moon, right? So they are not in contact, thank God. But there exists a force called gravitational force, right? Kenapa dia tukar-tukar ni? Alright. So, and then we have two charged particles here. This is called electrostatic force. Electrostatic force between two charged particles. One is negatively charged and the other is positively charged. When you rub a balloon with kain, right? When you rub a balloon with kain, you are removing some of its positive charge. So it becomes negatively charged, and then you put it at your hair. The hair sticks to the balloon. So that is electrostatic force. Because one is negatively charged, the other is positively charged. They attract with each other. That's why your hair sticks to the balloon. So that is electrostatic. It's a force that does not need contact. Your hair is attracted even without you touching the balloon. Even without the hair touching the balloon, they are attracted. Okay, so that is electrostatic force, doesn't need contact. The other one is magnetic force. Semua ni kita akan belajar later on. Magnetic, electrostatic ni, and gravitational. Okay, so untuk chapter ni kita belajar contact dulu. Push, pull, reaction. Okay, nanti saya cerita lagi. So the forces on an object is gravitational force or the weight of an object. We label this as capital W or mg. both are acceptable. So if I have an object here, okay, I want to label my free body diagram. Saya introduce sikit-sikit. So I want to label my free body diagram punya forces. So I start from the center. Where is my force of gravity? It's down here. It's always acting down. Even when you are having a projectile motion, it's acting down. Even when you're just sitting, it's acting down all times. So you can label this as mg. I like to label it as mg. You can label it as capital W if you like, boleh. And then if it is moving, it would have frictional force. So if it's moving to the right, ni movement dia, saya tak letak dekat object because this is not force, it's just movement, motion. Its motion is to the right. Therefore, my my friction goes the other way. So friction is labeled as small f. And then if I am in contact with lantai, my object is on the ground, I would have R. Nanti kita akan belajar macam mana nak tentukan R. So this is normal reaction force. You can label it as R or capital N. Dua-dua boleh, dua-dua acceptable. And then we have tension of tension of string. If this object is connected to a string, okay, let's not use this color. Ada cangkuk kat sini, lepas tu saya letak string. Okay, so this string that is connected to this object has tension. Okay, tapi disebabkan saya nak lukis free body diagram, saya akan cakap semuanya berasal di center of mass. Boleh. So that is my tension. So tension of string, label as capital T. And other direct contact force or push or pull, you can just label it as the magnitude. Contohnya, I'm dragging this box to the right, so I just label this as 10 Newton. Okay, kita letak dekat dia punya free body diagram. Nanti kita akan belajar lagi dengan detail. Okay, so this you just label as the magnitude. Or if you like, you can label it as F1, F2, F3 equals to whatever, okay, whatever magnitude that it is. So gravitational force, W or mg. Normal reaction force, R or capital N. Frictional force, small f. Jangan letak capital F, it's wrong. Frictional force always kena small f. Itu sahaja cara untuk membezakan frictional force dengan force yang lain. And then tension of spring is called capital T. Other direct contact force, push or pull, you just label it as the magnitude, or you can label it as F1, F2, F3 and define the magnitude. Okay, so now kita masuk kepada, ni tak payahlah. Okay, so the force of gravity is commonly known as the weight of the object. Your weight changes with the gravity. Okay, what do I mean by that, right? If you are at a different planet, the gravity is different. Your weight is dependent on this G. What is this G? This G is actually acceleration. How did it become acceleration? Because weight is a force and this is F equals to MA. G, the G is actually acceleration. So gravity, 9.81 meter per second squared is actually acceleration on that particular planet. In this case, the planet is Earth. If you're on a different planet, the acceleration on that planet is different, and we can calculate for the gravity on different planets using this equation. Tapi untuk memudahkan kita cakap okay, daripada equation ni kita dapat 9.81, so kita pakai je lah 9.81 ni. Tapi yang sebenarnya, ada lagi tapi tu. This 9.81 only applies if you are close to Earth. If you are close to Earth. Saya kat sini and then Amy kat sini. Amy cakap, doktor kita punya gravity sama ke? Sama sebab kita on Earth. Tapi kalau Amy terbang ke atas jauh, dia jadi satellite. Tiba-tiba Amy jadi satellite kan. Tapi okay lah, satellite lah. Amy tak jadi satellite. Amy is a person. So if there is a satellite, the gravity on that satellite ataupun the acceleration of that satellite with respect to the Earth is different because Dia jauh dari bumi. So the gravity of 9.81 only applies to objects, to people, to anything that is close to the Earth's surface. Kalau jauh, akan ada calculation lain dan akan ada acceleration lain. Therefore, 9.81 tak apply to that satellite ataupun ME. Okay? So 9.81 specifically untuk kita yang kat planet Earth. Okay? So we label gravity as this arrow. It starts from the center of the object. Let's say kita cakap pasal sekolah. Tak nak cakap pasal sekolah lah. Kita cakap pasal objek yang pelik-pelik sikit lah. Okay lah. Objek, apa nama dia? Pin. Bowling punya pin tu. Bowling punya pin tu kan. Kan dia macam ada bentuk pelik sikit kan. Okay. So if I wanted to draw the center of gravity, I wouldn't draw it down here. Because that is not where the center of mass is. So I'm assuming that the center of mass is around here. Kat sini mass dia berkumpul. Bukan mass dia berkumpul, dia punya center of mass lah nama dia. This is where it's most, how do I say this? Is center dia lah. Okay, nanti belajar center benda ni kemudian hari lah. Okay, so I would say, okay, this is the center of the mass of this object. Therefore, my free body diagram, when I'm drawing any forces, it should come from that point. So, kalau nak cakap pasal mg, okay, mg starts from here instead of down here. Jangan letak kat bawah ni. Salah Kena buat kat center. So, selalunya kita akan kasih symmetrical object lah untuk memudahkan kehidupan semua orang dan memudahkan saya untuk tanda. So, kita akan bagi objek yang symmetrical. So, kalau macam bola ni, you know that the center of mass is at the center because it's symmetrical. Therefore, your mg starts from there. This is how you draw your force. Wajib buat macam tu Okay. And then we go on to normal reaction force. Okay, I think I have questions or not? Tak nak sekolah, tak sekolah, okay. Lawak lah korang ni, okay. And then our next force is called the reaction force. Okay, bila reaction force ni berlaku, it's called the normal or the reaction. Okay, remember tadi kita cakap pasal mg or w. Now we're talking about normal force, N or R. So when does normal force happen? It only exists when two objects are in contact. It only exists when two objects are in contact. Bila bersentuh sahaja. Okay, bila bersentuh sahaja. Kalau tak bersentuh, tak ada reaction force. Okay, let's see. So this is a TV on a table. So the reaction force is perpendicular to the surface. The reaction force is perpendicular to the surface. What is perpendicular? Perpendicular means it's 90 degrees. This is also known as normal. Sebab tu nama dia normal. Sebab dia 90 degrees to the surface. So this is your reaction force and this is your weight. Ataupun weight TV ni lah. W equals to mg. Dalam kes ni dia label as Fg. Gravitational force. Boleh juga. Okay, so they label the reaction force as R, and R only exists 90 degrees to the surface and only when it is touching a surface. Now, when we have a car on a road, it is touching the road, right? And the surface is the road. Therefore, the reaction force starts from the center of the mass, center of the object, center mass of the object, and it is always 90 degrees. Okay. Kenapa kita letak dekat center of the object? Sebab kat situ senang nak approximate. Kalau kita letak kat sini, nanti macam kalau kita nak cakap pasal tension ke apa ke, contohnya kita nak tarik kereta kat sini, lepas tu saya tolak dekat sini. So dia macam tempat yang macam-macam tau. Kat sini ada force, kat sini ada force, kat sini ada friction. So bila force tu berselerak, susah nak nampak baik, susah nak estimate the net force. So untuk memudahkan hidup semua orang untuk mengira nanti, they come up with the free body diagram which focuses all the forces at the center. So kalau ada friction pun, okay, friction kat sini. Kalau ada mg pun, okay, mg kat sini. Kalau ada orang nak tarik pun, okay dia tarik kan. Tariklah. Tarik ke sini. So dia centerkan at one point so that we can see all the forces acting on that object. Kalau tak, kita kena tengok kat sini lah, friction. Kalau tak, kena tengok kat sini lah, saya tengah tarik kereta ni, kesian saya. Kereta ni tengah menurun kan, macam mana saya nak tarik. Lepas tu saya kena tengok, okay kat mana lagi gravity. Okay, gravity kat semua. Banyaklah kerja. So this is a good approximation when we use the free body diagram. So this is the reason why free body diagram is so important. It helps us approximate. Okay. The direction of normal is always perpendicular to the surface. 90 degrees, wajib. Okay, tengok kat sini balik gambar kereta ni 90 degrees to the surface. Surface dia adalah road. Okay, but MG tetap ke bawah walaupun atas road yang condong, road yang ada angle. Teruknya saya punya description. So MG is always going down. Tak kisah tak kisah. Macam mana pun mesti kena going down. Okay, so this is a box on a table. So you have your, kat sini dia tak label from the center of mass, dia tunjuk in general je. So MG is going down, W or reaction force is going up 90 degrees to the table. Okay, and then you have this box on a wall. The contact is here, so this is your surface 90 degrees to the surface. Ni tengah tolak, so ni F. Boleh label as F. Okay. And then we have this box on an incline. This incline has some angle. So dia punya contact surface is the incline. Therefore, the reaction force is here 90 degrees. Starts from the center of the object. Sama juga kat sini. Starts from the center of the object. Reaction force 90 degrees to the surface. Kat sini tak ada reaction force sebab dia tak bersentuh dengan apa-apa. Dia ada tali je. Tali tu nanti kita akan discuss kemudian. Tali ni pun ada force dia. So there's no reaction force over here because there is no contact. Dia tak bersentuh dengan siapa-siapa. This guy bersentuh, so ada reaction. Okay, so when an object is in motion or tends to move on a surface through a viscous medium, there will be a resistance to the motion. Ataupun geseran lah, geseran yang biasa kita dah belajar tu. So when you're moving or when you want to start moving, there is some friction before you move ataupun there is some friction that opposes your motion. This is due to the interaction between the object and its environment, and this resistance is called friction. So, okay, so the direction of friction is always opposing the motion, always. Tadi saya cakap pasal reaction. Reaction always kena ada surface. And then mg is always downwards. That was our condition for our forces, the two forces that we learned so far. Untuk force of friction, condition dia always opposing motion. Kalau box move to the right, your friction needs to move to the left. Okay, so kalau box ni bergesel dengan dinding, it's moving upwards. Where's the friction? The friction needs to go down. It's always opposing the motion. Always opposing the motion. Kena opposite, tak boleh sama arah. Ni condition friction. And then what if there is no... Okay, tak apa, saya introduce ni. So friction is F friction equals to mu R. Tadi kan saya cakap F ni label as small f kan. Tapi kalau kita label macam ni pun boleh juga F friction. But when you are drawing the free body diagram, it should be labeled as small f. Okay, so friction is equal to mu R. What is R? R is the reaction force. What is the condition for reaction force? Kena ada contact. So, therefore, friction is a contact force and kalau tak ada contact, tak ada friction. What is mu? Mu is the coefficient of friction and it depends on the surfaces in contact. Contohnya kalau lantai tu lagi kasar, coefficient ni akan lagi tinggi, friction pun lagi tinggi. Kalau benda tu licin, dia punya mu going to be small, friction pun going to be small. So mu ni depends on permukaan yang kita bergeser tu lah. Okay, so it's called mu. What is mu? Coefficient of friction. Saya dah cakap 3 kali at this point. Kalau ada orang tanya saya mu tu apa, tolong rotan diri sendiri. So what is mu? Mu is coefficient of friction. Macam mana nak tahu value dia? It depends on the surface. Typically they will give you, or you need to find it using the equation. Okay. So kita belajar 3 forces at this point. Let me wrap up sikit. Nanti kita take a small break. Okay, so what is N or R? Apa saya buat ni? Sekejap. So, kita ada 3 force yang kita dah belajar. Kita also belajar 3 Newton law. What is the first Newton's law? What is the first Newton's law?
Inertia.
Inertia. What does it say?
An object will remain at rest or move with a constant velocity unless acted upon by a force.
Yes, an object remain at rest or at constant velocity. Remain at rest or constant V unless acted on by a force. Sorry, tulisan buruk. Okay, and then from Newton's first law, kita tahu that P inertia is related to momentum. Momentum is a vector. And if you have a bigger mass, therefore your momentum is bigger. Therefore, your inertia is bigger. If you have a bigger velocity, then your momentum is bigger, then your inertia is bigger. Okay, inertia relates to momentum. And then what about Newton's second law? What about Newton's second law? What did we learn?
F equal to ma.
F equals to ma. When does this equation apply specifically? When our mass is
The M dia
Mass
constant.
constant. When it's not constant, dia equation dia jadi lagi panjang, plus V dm dt. Okay, so when we have a change in velocity, we have the acceleration, therefore we have force. Or if we have force, we will have a change in velocity on the object. Okay, it goes vice versa. And then we also talked about Newton's third law, which is, what is it? An object will apply equal but equal and opposite, right? F12 equals to F21. It means to say kalau saya pegang, saya tolak something, benda tu pun tolak saya balik at a same magnitude but opposite direction. So it's equal and opposite forces. Okay, so these are the Newton's law. And then we talked about forces of an object. Kita belajar specifically for external. Opposite attracts, okay. And then we talked about external forces. If I have a box on a table, how do I draw the free body diagram? I start from the center of the object, and then assuming we are on Earth, then this would become mg. And if it is in contact with the table, then I would have reaction force. If I'm trying to move it to the right, the motion is to the right, and therefore my friction will move the other way. This is my F. What is the condition for reaction force to happen? What is the condition? Apakah kondisi dia?
Two objects are in contact.
Haikal dengan Feli and Sophia said contact, betul. Tadi ada orang cakap pun saya tak tahu siapa, contact, thank you. So it needs to be in contact with something. Kena ada contact. What about mg? What is the condition for this guy? Apa condition untuk korang ada weight? Kena dekat earth. Yes, you have to be on earth. And what is the direction?
Downward.
Downwards. Always Walaupun kita atas satah condong, even though we're on an inclined plane, your mg is still mg going downwards. Walaupun dekat satah condong. And then what is the other condition for reaction force? Ada lagi satu about the direction. What is the condition for reaction force?
Perpendicular.
Perpendicular, yes. 90 degrees to surface. Okay, and what is the condition for friction?
In contact. The motion.
In contact and opposite in the motion, opposing the motion. In contact and opposing motion. So ada dua condition, in contact, oppose motion. Reaction kena contact, 90 degrees, mg have to be on earth and it's always down. Tak kisah macam mana pun. Yang ni kadang-kadang ada orang buat macam ni mg dia. Salah lah. Sebab tu saya tekankan kat sini. Always down. Tak boleh condong. Jangan condong ever. Okay. So that is your summary lah for what we have learned. Let's take a 7-minute break and come back at 8-minute break lah. Kita datang balik ke 11. 11 AM. Kalau ada soalan boleh tanya Okay, 7. Okay, 9, 10. Okay, let's continue. Hope everyone is back from their toilet break or snack break or drinking break. Apalah, datang balik. Okay, so let's focus balik. Kita nak belajar pasal friction now, friction in detail. So we talked about gravitational force or our weight. We talked about friction force and we talked about reaction force. And also we learned that these are all external forces, meaning to say that they happen outside of the body or outside of the object, right? Okay, saya nak introduce friction ni. There's two types of friction. The first one being static friction and the second one being kinetic friction. Okay, so static means you're not moving. Oh, cantik pula tulisan saya. And then kinetic friction means this is when it's moving. Okay, so as you can see here, the coefficient for static friction is greater than the coefficient for kinetic friction. From there, you can conclude that, oh, it takes more effort to actually move when you are at rest versus when you are already moving. So friction lagi tinggi bila kita tengah stop compared to bila kita tengah berjalan. And again, friction punya equation is F equals to mu R. The greater your coefficient of friction, the greater your friction. So kat sini, friction punya coefficient waktu tak bergerak lebih tinggi daripada coefficient bila kita sedang bergerak. So the friction is more when we're not moving actually, sebab dia akan cuba tahan kita daripada bergerak. Bila kita nak start bergerak tu, friction sangat tinggi. The tendency of movement actually already has resistance. You want to start moving, dah ada friction dah, sebab nak bangun tu pun ada geseran. Nak bergerak, berdiri tu pun ada geseran. So that is your static friction. And kinetic friction is the one that we regularly see or kita dah biasa tengok. For example, car moving on a road, the tires, the contact of the tires with the road bergeser, that is the kinetic friction when it's moving. And then we know that when we are touching an object and the object slips, walaupun dia slip, ada juga friction, sebab kalau tak ada friction dia akan jatuh dengan sangat laju, kalau ada friction dia jatuh slow sikit. So everything sebenarnya ada friction lah, unless it's like super smooth, then there won't be any friction. Nak pegang pen pun ada friction, kalau tak ada friction jatuh, it will slip out of my hand. So that is the function of friction. Okay, so static friction acts to prevent object from starting to move. And kinetic friction tries to oppose the motion of object by slowing it down. And then direction dia always opposing motion. So if your velocity is to the right, your friction is to the left. Okay, so as theta increases, F static decreases, F down increases. So this is the equation for F static. F static dengan F kinetic punya equation sama. F equals to mu R. Tapi perbezaan dia is this mu untuk static ada S. Untuk kinetic, nama dia mu K. Mu K R. Okay, mu K R. So that is the difference between static and F kinetic. Kalau tengok jadual tadi pun, this is called mu S and mu K. So that is how you differentiate between static and kinetic. If they did not label S or K, then you just take it as it is, as just the coefficient of friction. Tak payah kisah dia static ataupun moving. Okay. So when F static is greater than F down, okay, just bear with me on this explanation first. If F static kan kat sini, benda ni dekat satah condong kan? Inclined plane. Don't know if that's the right word. It's on the inclined plane. Kat sini ada angle theta, right? So tendency of this object is dia mesti nak ke bawah kan, sebab senang untuk menggelongsor ke bawah daripada ke atas. So the tendency of movement is downwards. Tendency of motion is going down sebab itu lagi senang daripada dia kena panjat naik atas. So when F static, bila friction is greater than F down, when F static is greater than F down, therefore the object will not move. Sebab friction ni dia tahan daripada menggelongsor. So bila benda yang tahan ni lagi besar daripada force yang menggelongsor, therefore dia tertahan lah kan, dia stop moving, dia tak bergerak. But when F down is equal to F static, the object is at the limit of static friction. The object is at the limit of static friction. Okay, again, mula-mula if our F static is greater than force untuk menggelongsor ke bawah, therefore the object will remain at rest ataupun not moving. But when F down is when F down is equal to F static, it is at the limit of static friction. And then when F down is greater than F static, maksudnya F ke bawah lagi besar daripada F static, friction static tu, then dia akan menggelongsor. Bila dia start menggelongsor, then F friction becomes F kinetic. Bila dia start menggelongsor je, kita punya friction jadi friction kinetic. So tu ada limit of static friction ni. Lepas je limit of static friction, kita pakai coefficient kinetic friction. Lepas je limit static friction, kita akan pakai coefficient of kinetic friction. Okay, so this limit is the boundary between pakai static versus kinetic. Okay. Faham ke tak? Oops. Confused ke faham?
Okay.
Okay lagi Okay. So F down ni force yang ke bawah je tak ada apa-apa. Don't think anything of it. Just anggap dia force untuk ke bawah saja dulu buat masa ni. Okay. So kinetic friction when theta is further increase. Theta is theta C. Nanti kita cakap pasal theta lah. Kita cakap pasal F dulu. So bila kita condongkan lagi satah tu, kita punya F down ni dia akan jadi lagi besar sebab daya untuk ke bawah tu lagi besar kan, lagi senang dia nak jatuh. So F down jadi lagi besar daripada F kinetic. Bila dia lagi besar daripada F kinetic, dia akan menggelongsor ke depan. Mula-mula tadi F down less than F static. Yang ni dia tak bergerak. Kan? And then F down equal to F static. Kat sini dia tak bergerak lagi, tapi dia dah sampai limit dia. Dia macam nak gerak tapi tak gerak lagi. Dia dah sampai limit dia lah. Limit nak gerak. Limit of static friction lah. Limit of static friction. And then bila limit ni dia dah cecah lebih daripada limit of static friction ni, maksudnya dia dah lebih daripada F static ni, dia punya F down ni akan greater than F kinetic. Dia punya F down ni of course lah akan greater than F kinetic sebab F kinetic selalunya kurang daripada F static. So bila F down greater than F static, kenapa lah saya pakai hijau ni? F static, dia akan move. Tak gerak lagi kat sini tak gerak lagi. Dia akan move. And then tiba-tiba dia cakap okay, F down must be greater than F kinetic. Sebab F kinetic is always less than F static. So when F down is greater than F static, then it is also greater than F kinetic. Therefore, it will move down. It will menggelongsor. Okay, the equation for F kinetic is ejaan salah kat sini. F kinetic is mu KR. What is R? R is the reaction force. So bila kita cakap pasal friction is less than F down, friction is greater than F down, semua ini berkait dengan theta of the inclined plane. Dia berkait sebab value ni akan berubah. Value of R, which is this guy, akan berubah mengikut theta. So bila value dia berubah mengikut theta, then you would have these different boundary conditions. Then you would have these different conditions. Okay, so macam mana kita dapat R equals to mg cosine theta? Nanti kita akan belajar. Okay, so usually the coefficient of static friction is greater than the coefficient of kinetic friction. I told you before, kalau F static is always bigger than F kinetic. Okay, nanti kita cakap pasal ni. Okay, so direct pull or push. Forces with direct contact with the object. Kena ada contact kalau nak push dengan pull. So tarik. Yang ni push. Ya Allah, kenapa gambar macam ni? Okay, so this is pull. Now this is push. When we are pushing an object at an angle, kita ada reaction force. Tapi macam mana kita nak resolve this force to be in the same plane as our reaction force? Reaction force kita always perpendicular to the surface. So this is our reaction force. Tiba-tiba force ni arah ni pula. Macam mana pula tu? So if we wanted to know the forces that is parallel or perpendicular to the reaction force, kita kena resolve. Macam mana nak resolve? Macam biasalah. So this would be F cosine theta, and this would be F sine theta. F in this case is, we don't know, maybe it's 10 Newton. So 10 Newton sine 40, 10 Newton cosine 40. So you would have a force on the right, going to the right, that is coming from the pushing force. And you would have a force going upwards that is coming from the pushing force, and value dia F cosine theta. So let's say you are pushing this box by 20 Newton. Okay, so this 20 Newton, when you resolve it, cosine 40 times 20 Newton. So you are actually pushing 15.32 Newton upwards, and you are pushing sine 40 times 20. You are pushing by 12.86 Newton to the right. Okay, so if they ask you what is the force that is opposing the reaction force, you can say, oh, it's F sine theta equals to 12.86, assuming that this is the only force happening in this situation lah. So you would say, okay, R is opposing F sine theta, which is 12.86 Newton. Okay, so this is how you resolve the forces. So if I were to draw this in the free body diagram, I would draw it like this: F cosine theta, and this is F sine theta. And F sine theta is opposing reaction force. Itu saja. Kalau kita nak cakap friction, boleh. Friction, let's say is going upwards and going to the right. Assuming it's going upwards, kita cakap friction kita ke bawah. Okay, assuming motion kita ke atas. Ini yang nampak logik. So friction kita ke bawah. So this is how we draw the free body diagram. Do you need to draw this thing over here? No, you don't have to. It is enough that you draw it over here because it means the same thing. Ini saya nak tunjuk je tadi. So you would write 12 point apa entah tadi Newton equals to berapa tadi 12 blah, blah. Tak tahulah. You can write the magnitude or you can just say F cosine theta, assuming that you know what F is. Okay, so that is that. And then we go on to our next force, which is tension, called capital T. The force exerted by a rope, string or wire. So anything yang panjang lah. So kat sini dia pakai rope. The direction is always towards the center of the rope. Center kat sini. Tension ke sini. tension ke sini. Nampak macam ada dua, but it's actually the same force. So kalau tension kat sini 10, sini pun 10. They are the same force and they are acting towards the center. And if this guy is exerting a tension of 20, this guy is also exerting a tension of 20 Newton on the rope. Rope punya tension. Apa yang diorang tarik tak tahulah. Maybe dia ni tarik by 50 Newton. Maybe dia ni tarik by 40 Newton. Tapi tension on the rope is 20 Newton on both ends. Dia kena sama. Sebab dia acting, it's basically the same thing, acting towards the center. So tension kena sama. Unless ada cabang kat sini, then dia kena divide the forces into its components lah. Tapi kalau satu je, kalau it's just one dimension, then you would say, okay, the tension is the same. Okay, so the force exerted by a rope, string or wire direction is always, okay, this is the same thing. So again, it always acts towards the center. This is tension force. This is also tension force. Ni pun ada string juga, ni pun ada string juga. Dua-dua tension yang sama, equal. Like I said, equal ni kalau dia satu dimension je. Kalau dia banyak dimension, then you would have to resolve it. Okay, so a tension force exerted by a rope, string or wire sama. If the pulley is smooth, condition. If the pulley is smooth, let me use a different color. Benda pakai warna sama. If the pulley is smooth, okay, saya highlight ni. If the pulley is smooth, then the tension on both sides are equal. Tadi saya cakap one dimension, tension sama. Tapi ada condition lain. Kalau pulley smooth, what is pulley? This guy. If benda ni tak ada friction, if it is super smooth, then your tension would be equal and towards the center of the rope or string. Ini string kan? Center dia tetap kat sini walaupun pelik. So it's still acting towards the center. If the pulley is smooth, the tension is equal. Okay, so again, if the pulley is smooth, the tension is equal. This T is equal to this T. For this case, where is the tension untuk objek ni? Ni tak ada pulley. Dia ada dua string. So the tension is here, T1, T1. This is the center. T1, T1. This is T2, T2. So this is the center of the string. You have two strings. So you would have two different centers. So you would have two different tensions. Walaupun dia originate daripada sini, tapi string dia ada dua. So you would have T1 going here, T2 going here. If I wanted to know what is the free body diagram for this, what is this? Frame. Tak tahu lah frame ke apa kan. So I would draw it from the center. Okay, abaikan gambar-gambar ni semua. I would draw from the center. Tension 2, tension 1, mg. Do I have friction here? Do I have friction? Dun, dun, dun. Friction ke tak ada? Apa condition friction?
On the ground.
On the ground. Yeah, so there's no contact here, so there's no friction. What about the normal force? Do we have a normal force or not? Reaction force.
No.
Tak ada because there's no contact. Again, friction dengan normal force, dua-dua kena ada contact. Baru dia jadi. Kalau tak ada contact, tak ada lah, okay? No contact juga, betul. So we only have tension and also the weight gravitational force. Gravitational force is a non-contact force, therefore it always exists even though there's no contact. Okay, so now baru dia nak cerita pasal free body diagram. Tadi saya dah cerita siap-siap dah intro. A diagram to represent all the forces acting on an object. We treat the object as a particle. That is why when we have an object, we just put a dot and put all the forces dekat dot tu. Because we treat it as a particle, it makes our approximation easy. All forces on the object act at its center of mass. Only forces acting directly on the object are included in the free body diagram. Contohnya, forces yang dalam objek internal macam vibration of atoms, kita tak masukkan dalam free body diagram because it's inside. We only put the external forces on the free body diagram, and then we always indicate the direction of force. Let's say awak draw macam ni, dan macam ni friction, and then apa reaction form macam ni, tak ada arah, there's no arrow here, it's wrong. You can give me the magnitude, semua betul kat sini. Awak tulis mg equals to 100 Newton, dia sangat berat orang ni, friction dia 10 Newton je, resistance dia tak berapa berat. So even though your magnitudes are correct, if you don't give me the direction, it's wrong. Force is a vector, always have the direction and magnitude. Always indicate the direction, okay? Okay, so again, so this guy is pulling a crate, he is moving to the right. We have friction opposing the motion. Opposing motion. Is this a kinetic or static friction? What is it? Is it moving or is it stopped?
Moving.
Kinetic. It's moving, right? I told you it's moving just now. So it is kinetic. Kinetic apa? Moving lah. Kinetic kan? Kinetic energy, moving energy. Okay, so it is mu, apa tadi? Kinetic. So mu r. So F equals to, sorry, mu k, mu r. Mu k r. Coefficient of friction, kinetic coefficient of friction. R is the normal force. Apa R? R kat sini lah. That is why you have to draw the free body diagram, because you have to identify what is R to know what is F. Or you have to know what is F to know what is R. Okay. So penting lah dia berkait semuanya. And then R is always 90 degrees with respect to the surface. Kena bersentuh and kena 90 degrees. Wajib. And then pulling force, this person only labels it as P. I would prefer to label it as FP. We know that it's a force. Kalau P ni apa? Tak tahulah kan. So FP lah, better FP. Force pulling. And then W equals to mg. You can write it as mg, you can write it as W, or you can write it as W equals to mg. Dua-dua boleh. It means the same thing. Okay, indicate the direction of forces. Kat sini dia letak arrow semua ada direction. Okay, example 3.1. Draw the free body diagram for all cases below. Okay, let's do it. So we start with the center of mass. What do I have here? What do I have here?
mg.
mg.
mg
Okay,
downward.
mg is going
Downward.
downwards. Okay, please tell me the direction sekali. What else do we have?
Normal force.
Normal force.
Normal force. Direction?
Upward.
Upward 90 degrees with respect to the, perpendicular to the table. So it's 90 degrees. We draw our imaginary axis. It's 90 degrees. We label this as R or capital N. What else? Friction. So it's saying friction. Okay, direction please. What is the direction here? What is the tendency of this box? Does the box tend to the right? So it should be opposing the motion. So friction is this way. If it has the tendency to move, but it's not moving yet, what is my equation for friction? It has the tendency to move, but it's not moving yet. What is the equation for friction? Static or kinetic?
Mu
Static.
SR.
Mu SR.
Okay.
So it's static, dia tak gerak lagi, so we use mu SR. If it is already moving, then you use mu KR, okay? So it's static friction right now because it's not moving, but it has the tendency to the right. Okay, not moving yet lah. Contoh konon-konon lah dalam cerita ni. Not moving but tendency to the right sebab kita ada orang tarik dia. So dia ada tendency untuk ke kanan tu. Okay, what else? What else? Tension force. Okay, what is my tension force? What is the direction? Direction? So, tak ada orang nak jawab direction ke? Okay. 30 degrees. Okay, 30 degrees with respect to apa? Below the x-axis, above the x-axis, north of
Above.
the above
Above.
the x-axis. Okay, so it's 30 degrees and I label it like this. Tension 30 degrees. Wajib ke tulis angle ni? Yes, wajib because it gives me the direction. If you just say, okay, tension is 30 degrees. 30 degrees apa? Below axis. Apa tu? Below the negative x-axis. Boleh. 30 degrees can mean anything. So you always have to specify dalam free body diagram ni. Lukis angle tu. Okay, so it's 30 degrees. Do we have anything else here? Kita dah belajar reaction, friction, gravity, tension. Is there anything else? Tak ada kot. Okay, so next one. We have a traffic light. Okay, we have a traffic light. So this is my center of mass. What is the forces acting on this traffic light yang tergantung ni? So this is slightly harder lah.
mg downward.
mg downwards. Do we have friction?
No.
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 Contact. Do we have reaction force?
No.
No. Do we have tension on this traffic light?
Yes.
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 Which direction is that? So kalau kat sini, direction dia is upwards. Tak nampak pula. Saya nak pakai warna lain daripada hitam. What colour? Purple. Okay, purple. So the tension is like this and this is the mg. So this is specifically for the traffic light. So if they ask you, okay, draw the free body diagram at this point. So you would have T2, T1, and T3, whereby T3 is equal to the T3 over here because they come from the same string. T3 over here is the same as the T3 for the traffic light because the tension of the string comes from the same string. Therefore, they are equal. Sepatutnya. Okay, faham tak? So T3 kat sini, T3 kat sini sama Okay, let me draw that again. So sama je macam tadi kita tarik bila kita ada dua orang yang menarik tali. Seorang kat sini, seorang kat sini. Kita ada tali kan? So tension acting towards the center of the rope. Sama juga kat sini. Tension acting towards the center of the rope. So kat sini T3, kat sini pun T3, kat sini T, kat sini T. So sama kat sini. So T3 untuk traffic light adalah sama dengan T3 untuk this string. Tapi T3 ni balanced out by mg. This guy T3 is balanced out by T2 and T1. Bukan balance out lah, dia ada kawan-kawan dia tu. Nanti kita akan cakap pasal balance out kemudian. So, kita tak masuk lagi yang tu. Okay, so T3 ni untuk traffic light. Tapi T3 ni untuk string yang ada 3 cabang ni. Okay. Next one. Ada lagi. Ada condition kan pasal tension ni. What was the condition for a pulley for to have the same tension on both ends? What was the condition?
Smooth.
No friction. This guy has to be smooth. Okay. And this is the T. This is the T. This is T1. Sorry. This is T1. And this is T2. This is also T2. Okay, so it's acting towards the center of the rope. Sorry. Apa saya mabuk? The equal. T sini sama dengan T kat sini. Sorry. So T1 is equal to T1. Okay, so it is from the same rope. Tak ada cabang kat sini. It is from the same rope. There is no friction. No friction. It is smooth. Therefore, it is a single, I would say a single entity lah, single string. Kalau ada friction, then akan ada masalah sikit kat situ, dia akan bahagi kepada dua. Tapi kat sini tak ada friction, it's smooth. So, kita anggap dia sebagai satu tali. Therefore, tali ni, the tension is acting towards the center of the rope. Okay. So, ni yang senang lah. There's no friction, it's smooth. And for this guy, oh sorry, tak habis lagi. So, this is the tension for A. We have mg here. What else do we have?
R.
R, okay, 90 degrees to the surface. So this guy is being pulled by a mass. What is its tendency to move? Is it to the right or to the left? So mana yang lagi berat sebenarnya? Oops. Ke mana dia nak tarik tu? Dia nak tarik ke kanan ke dia nak tarik ke kiri? Anyone? No one knows? Sebab A lagi berat. Kiri, kanan, kiri. Okay, kiri. So R. Feli is saying R. Bukan. Feli tak jawab pasal soalan tu. So Syeki said A lagi berat. Fifa cakap kanan, kiri lagi berat. So A lah, semua orang nak jawab A. Okay, so memanglah A lagi berat 5 kg kan. But this guy, saya cakap. So kalau kita bayangkan pun, kalau kita ada orang yang tengah tarik benda ni, tengah tarik, mestilah benda ni nak gerak ke kanan kan, walaupun dia lagi ringan. Tendensi tu ada ke kanan. Tendency to the right. Kita ada tendensi untuk ke kiri tak? Boleh tak kita ke kirikan objek ni?
Tak boleh.
Tak boleh kan?
Boleh kan? Tak
Kalau
boleh.
boleh pelik lah. So tendensi untuk objek ni bergerak adalah ke kanan sahaja because kita ada benda yang menarik dia ke bawah. Benda ni tak ada tarik-tarik ke tepi. Dia ada ke bawah mg je. Tarik-tarik ke tepi tu friction je lah. So tak ada benda yang menarik ke tepi. So nak kata ada tendensi to the left tu tak ada lah. So dia hanya ada tendensi to the right ataupun tak bergerak. Right or V equals to 0 lah. So that is the tendency here. So if it has the tendency to the right, therefore my friction for A is to the left. And we have the R macam biasa, 90 degrees perpendicular to the surface, and this is mg. And we have the tension here, T. Okay, and for this guy, kita do object, therefore we will have two free body diagrams. Remember, free body diagram is at the center of the mass. If you have two masses, you would have two center of masses. So in this case, the center of mass is here. This is your mg, and this is your T1. T1. Sama equal sebab smooth. Okay, so you only have mg here. This is your free body diagram for A. This is your free body diagram for B. What time is it? Okay. And then for this guy, this is also smooth. Kita memang pakai smooth pulley je untuk kita punya syllabus. Here they say that we have acceleration going upwards and acceleration going downwards. So kita tak belajar lagi pasal ni. Tapi kalau saya nak lukis dia punya free body diagram, kita tak belajar lagi acceleration. Saya akan lukis macam ni, mg. This is M1, right? Because this is mass number 1. This is mass number 2. We have tension. Since this is a smooth pulley, our tension should be equal. T1 equals to T1. And you have your acceleration going upwards and acceleration going downwards. Acceleration ni is not part of your free body diagram, but you need to label it. Nanti kita akan belajar lagi lah pasal ni. acceleration is not a force, it is acceleration. So you just label the direction and also outside of the free body diagram lah. Okay. Okay, so now we talk about net force. Bila kita nak sampai example lah? Penat lah cakap. Okay, kita buat example dululah. Consider a block at rest as in figure. Indicate the forces acting on the box in the diagram and draw the free body diagram for the box. Okay, so kat sini, can I ask, alamak susah pula nak lukis kan? Okay, kita jawab je lah soalan ni terus. So consider a block at rest. So it's not moving not moving. Indicate the forces on the box in the diagram and draw the free body diagram for the box. So mula-mula dia suruh, okay, indicate dulu. Letak, bagi tahu je lah dulu apa yang ada forces. So kita ada, what do we have? We have reaction. What else do we have?
mg,
mg,
J,
Gravitational force.
friction,
Great.
friction,
We have friction. So how do you know it has friction? It's not moving. How do you know there's friction?
contact,
It has contact, yes. It has contact, and at rest pun kita ada static friction, right? So memang ada juga. Okay, what else? Lagi tak? Tadi dah. Okay, so if I were to draw the reaction, it should be 90 degrees to the plane, to the surface. So it's 90 degrees. Kena reaction. Tak tahu nak cakap berapa kali ni. Tapi reaction kena 90 degrees to the surface. 90 degrees to the surface. Nampak ni kan? Okay, 90 degrees. Wajib jangan lukis lain daripada ni. And then the next one. Friction. Friction, the tendency of this object to move is to the right. Sebab dia nak menggelongsor kan? Kebiasaannya, kalau ikut logik pun lah, kalau kita letak objek atas gelongsor, dia ada tendensi untuk jatuh ke bawah. Dia tak ada tendensi untuk naik ke atas unless kita tolak dia. Tapi kita nak cakap, kalau tak ada orang tolak, dia nak ke kiri ke kanan? Dia nak jatuh ke bawah kan? So tendensi dia adalah untuk jatuh ke bawah. Therefore, kena ada friction yang menghalang penggelongsoran ni dari berlaku, and that friction is called static friction. So static friction yang menyebabkan kotak ni stay at rest, tak gelongsor. Kalau tak ada friction, licin, dia gelongsor lah. Sama juga macam pen, saya pegang pen. This pen, it has static friction on my fingers supaya saya boleh pegang at rest. Kalau static friction tak ada, then it would slide off my hand. So always ada static friction and the tendency for this pen adalah menggelongsor ke bawah sebab kat situ ada daya gravity, so that is where it wants to go off lah, to gelongsor. So macam mana saya tahu gravity akan menarik ke bawah ni? Ada cara dia. Kita tak resolve lagi kita punya mg. So our mg always goes downwards, right? But in this case, how do we know there is a component to the right? Kita resolve lah macam biasa. So mg, kalau kita ada angle theta kat sini, then our mg would have a theta over here. And this would become mg cosine theta, and this would become mg sine theta. Again, if your theta is here, the theta is over here. Macam mana? Ada cara dia. Saya tak ingat. Nak kena buat betul-betul. So this is 90 degrees. This is something 180 tolak 90 tolak this theta. Adalah cara dia, saya tak ingat lah. Kena ingat balik. Okay, tapi saya selalu ingat shortcut dia. Okay. This is what I'm guilty of lah. Theta kat sini is equal to the theta over here. What is the theta if the theta is like this? Then your mg, mg is like this. This is your theta. Macam ni So korang ingat je satu gambar, lepas tu korang flip lah dia macam mana pun, flip. Kena ingat je. Kalau nak buat sendiri gambar ni sampai dapat theta pun boleh. Ada cara dia, it's all math, which I don't like. So theta kat sini, theta kat sini. Kalau theta kat sini, dia kena in between the y-axis punya component tu. This is your y-axis component, right? Assuming this is your y and this is your x. Dia in between the mg and the y-axis component. So you put your theta there. Anything that the axis that touches the angle gets the cosine, walaupun dekat y-axis. So it gets the mg cosine theta and this is mg sine theta. Kenapa saya cakap this is your y and this is your x? Sebab itu memudahkan hidup saya untuk cakap this is x and this is y. Nanti kita nak resolve nanti, kita akan resolve with respect to the y in this way, resolve with respect to the x in this way. Ataupun we can call this as perpendicular component and parallel component. Boleh. Okay. So again, if my theta is over here, the theta is in between the mg and the y-axis component, y-axis of the object of the gravitational force. Theta kat sini, this is my y-axis, this is my x-axis, y, x. Therefore, my theta is in between mg and the y-axis component of mg. Okay, theta is there. So the y-axis component gets the cosine mg cosine theta, mg sine theta. Everyone okay with this one? Kita buang ni. Okay tak dengan gambar ni? Semua faham tak?
Kurang.
Okey lagi doktor.
Yeah. Ada soalan tak so far on anything related with what we have cakap? Dia macam Pythagoras ke doktor? Ya kot, saya tak ingat lah. Saya kena derive balik equation dia. Tapi taklah susah pun, tak susah pun. F down. Faham. Okay, tak ada soalan Okay. Again, kalau theta dekat sini, theta kena in between mg and y-axis component. Tu je cara saya ingat. Kalau nak buat sendiri gambar dia boleh derive. This is y-axis component, this is x-axis component. Kenapa saya resolve? Sebab saya nak tahu apa yang selari dengan friction, apa yang selari dengan reaction. So that nanti saya nak kira-kira untuk force nanti senang lah. So sebab tu saya resolve. Okay. So dah settle lah example 3.1. Okay, example 3.2. Okay, ni korang buat sendirilah. An object moves on the floor to the right. Okay, it moves on the floor to the right across a frictional surface when 50 Newton force is applied to it. Okay, so ada 50 Newton force applied. The object encounters 10 Newton of frictional force and the weight of the object is 80 Newton. Determine the normal force, net force, coefficient of friction and mass. Alah, tak boleh buat lagi sebab korang tak belajar lagi ni. Okay, so kita buat sama-sama. Saya dah penat ni. Okay, tak apa. So, okay, kita cakap the object is moving to the right. Okay, this is the motion. Okay, and then dia cakap ada frictional surface. So if motion is to the right, frictional force is to the left. And F is equal to 50 Newton. Okay, that is your first one. Yay. And then the object, silap. 10 Newton is frictional force. Saya salah baca. Sorry. Okay. An object move on the floor to the right across a frictional surface when 50 Newton force is applied to it. So bila kita apply a force and dia punya movement to the right, maksudnya force kita ke kanan lah kan. Kita apply, kita tolak something and dia bergerak ke kanan. Maksudnya memang ke kanan lah force kita kan. Kalau kita tarik something tapi dia bergerak ke kanan, peliklah pula kan. So kita kena push lah. It should be a pushing motion towards the right. So this is F. F equals to, I just label this as F, 50 Newton. Okay, so that is your F. This is small f. Nak kena lukis cantik sikit. Small f. Okay, ada beza F small dengan F besar. Lepas tu kita ada weight. mg equals to 80. The weight of the object is 80 Newton. We also have reaction force, but we don't know what it is. Reaction force. Okay, so assuming that this guy is only moving to the right, assuming it's only moving to the right, it's not flying or whatever, it's still maintaining contact while waktu dia bergerak ke kanan ni, it means that there is no acceleration going upwards or downwards. Tak ada. Acceleration is zero. Sebab dia tak ada, dia tak melayang-layang kan. So, tak ada lah acceleration. There's no pushing or pulling force except for reaction and mg. And then it's moving to the right, so we can assume that maybe there is some acceleration to the right, positive acceleration, maybe, assumption. Okay, so now it's asking what is the normal force? So if there is no acceleration that is pushing the box to fly or whatever, it's maintaining contact at all times, we can say that R plus mg is equal to 0. We can say that because it's not flying. There's no acceleration. How did I get this equation? It is actually net force. Net force. Apakah total force dalam y-axis? The total force in the y-axis is R plus mg bersamaan dengan kosong. If my fy, net fy equals to ma, then my box would be flying. But in this case, my box is not flying. Therefore, this guy becomes a 0 and R plus mg is equal to 0. So now I can say, oh, if this guy is a 0, then mg is equal and opposite to R by Newton's third law. So R is equal to minus mg, meaning to say it has the same magnitude but in opposite direction. We know what mg is. Mg is 80, therefore reaction is 80 Newton. But in this case, it looks like off sebab reaction kita ke atas, mg kita ke bawah. So what can we say about this? We can say that R, kita nak cakap R as positive and mg as negative sebab mg ke bawah. So when I rearrange this equation, R becomes positive mg and R becomes 80 Newton. So the sign for my equation depends on the direction. R ke atas positif, mg ke bawah negatif. Kenapa dia equal to 0? Sebab dia tak melayang. Acceleration 0. So it's equal to 0. Total force dekat dalam y-axis adalah kosong because dia tak melayang. Okay, so now we can't say the same thing about the x-axis, right? Because it's moving to the right. There has to be some acceleration, I'm assuming. Okay, so untuk net force in the x-axis, okay, I say that oh sorry, kita kena cakap pasal friction dulu. So friction, dia tanya what is the coefficient of friction between the floor? So I know that my friction is 10 Newton. Okay, it's 10 Newton. How can I find the coefficient of friction? Is there a way? What is the equation for friction? It's mu R. Do we know what our R is at this point? Do we know what our R is? Tahu ke tak tahu? Divide by R. Okay, so F divide by R. Feli is Haikal cakap saya rasa saya dah hilang. Tadi tu bila tu? Oh, baru lagi. Jangan hilang lagi, sikit lagi. Kita habiskan example ni je. And then F is equal to 10 Newton, right? We don't know what our mu is, but we know our R. Kita solve tadi. Kita cari reaction force kita. So this guy is 80 Newton. Therefore, my mu is F over R, or 10 divided by 80, or 1 over 8, or whatever that is lah. 1 over 8 lah, okay? What is the unit for mu? What is the unit for mu? Tadi saya lupa nak cerita. So kalau tengok equation ni, what is the unit? Eja
Tak ada
mu
unit
tu
eh?
macam mana?
No unit, no unit.
No
Tak ada
unit.
unit kan? Sebab ada
Ada
cancel.
unit sebab
Dah cancel.
Cancel.
N
it
dengan
cancels
N.
out. Yay, korang dah tahu pakai dimensional analysis. Correct. So mu does not have any units because eventually it cancels out. So 1 over 8 tak ada unit. So bila kita pakai F equals to 1 over 8 tak ada unit, darab dengan reaction force which is Newton, we end up with Newton. Correct. Okay, so now kita dah tahu mu, cara cari mu. Mu macam mana nak eja? Saya pun tak tahu. Mu, tak tahulah, korang Google lah. Saya tak tahu. I also don't know. I'm not even physics major. Okay. Okay, so 80 Newton, coefficient kita dah settle, normal force kita dah settle. Oh, kita nak cari mass. Okay, so mass. W equals to mg, right? So kita tahu g apa, kita kat earth. So that's pretty easy, right? 9.81. This is 80 Newton. So divide by 9.81, you get your mass. So that's pretty easy. Tak tahu juga, saya duduk kat earth lah, cari planet lain. So 80 divided by 9.81 So you get your weight as 8.15 kilogram. SI unit always. Okay, satu lagi. Kita ada masa tak? Okay, ada lagi. Tapi sebenarnya kalau saya pukul 1 kan, saya tak adalah. Saya buat 2 jam je, pengsan semua orang. Okay, so mass kita dah dapat. Reaction force kita dah dapat. How did we get our reaction force? Kita equatekan the net force in the Y equals to 0. Kenapa saya pilih 0? Sebab this guy is not moving up, it's not moving down, it's maintaining contact at one point walaupun dia bergerak ke kanan, tapi dia in the Y axis, dia tak ada atas bawah tak ada dia satu tempat je dalam Y axis. So kita cakap okay, this guy has 0 acceleration, therefore 0 acceleration equals to 0 force, net force sama dengan kosong. Apa yang ada dalam Y axis, positive R tolak mg. Kita tak tahu R apa, but we want to know what is, we know what is our mg, so R equals to mg sama dengan 80. Opposite direction to the mg. And then weight, kita dapat mass daripada W equals to mg equation. This is easy, I think I can just wrap this off. Now we're talking about net force. So net force tadi kita cari in the Y. What about in the X? Fx. So we have, kita tak tahu dia punya acceleration macam mana at this point. So we just add in what is in our equation, assuming that to the right is positive and to the left is negative. Sebagai warna lain. Okay, to the right is positive and to the left is negative. So positive 50 Newton minus 10 would give me 40 Newton. Okay, so kita nak cari acceleration ni. So F is always equals to MA. So kita tak tahu dia gerak ke tak. So kita letak dulu MA. Kenapa saya sebut hijau? Hijau is like a bad colour. MA. So it's 40 Newton. And we know what our mass of our object is. Mass ni tak kira axis Y ke, axis X ke, mass is mass. It's a scalar quantity. So here mass is berapa tadi? Alah, kita dah kira tadi. Mass is 8.15 kilogram. Okay, so we can find out what is our A. So 40 divided by 8.15 will give you acceleration positive. So 40 divided by answer 8.15 tu dapat 4.91 acceleration positive to the right. To the right. Okay. Okay, ni first time saya cerita pasal net force kan. Jangan panik lagi lah. Baru je masuk. Okay, so I think I'm going to end class here. Ada soalan tak pasal net force? Okay, kita kejap net force ada fx dengan fy. Tak apalah, nantilah next class. Susah nak cerita. Ada soalan tak berkaitan dengan apa yang kita buat untuk example ni? Macam biasalah, ada fx, ada fy, nanti kena cari magnitude f, kena cari direction f. You have to add the x and y together to get the vector f. It all comes back to vectors. Maksudnya net force tu net acceleration ke? Kita akan gunakan equation net force untuk tentukan sama ada dia ada acceleration ataupun tak ada. Tapi kita akan kena tengok dululah situation dia. Kalau ada motion, kita boleh assume lah ada acceleration. Kalau tak ada motion dalam y-axis, kita cakaplah acceleration equals to 0. Okay, nanti kita akan go through more examples and hopefully our understanding becomes better on this. Okay. Oh, Amy cakap agent mu is mu. Mu. Okay, saya pun tak tahu. Okay, that's good. Tak ada soalan Everyone's okay or just like dying inside? Tak apa, baru je belajar ni. Nanti insyaAllah faham nanti. Dying, yes. Waktu saya baru belajar pun sama. Net force ni is a new concept. So it's totally normal to feel that way. Okay, tak ada soalan Okay, bye guys.
Doktor nak tanya.
Okay.
Nak tanya kalau yang macam yang ni bukan topik 3 dia chapter sebelum ni, macam mana nak tahu U dia tu sama dengan kosong ke ataupun dia ada dia punya nilai?
Chapter 2.
Chapter 2.
Oh, kalau U
Boleh
tu soalan akan bagi. Kalau dia cakap projected horizontally, then your UX ada value, your UY is 0. Tapi U ni velocity dia bukan acceleration. Okay.
Oh, okay. Thank you, Doctor.
Okay, welcome. So, any other questions? Tak ada Okay. Alright, have a great rest of the day. Don't forget to get your lunch and take care. Bye everyone.
Thank you, Doktor.
Thank you, Doctor.
Bye.
Bye-bye.
Welcome. Bye-bye.
Sorry, Doktor.
Bye.
Sorry, Doktor tadi saya masuk lambat sikit tadi.
Okay, tak apa. Bye. Jangan lupa attendance.